Okay, so now we have some foundation for discussing the full Kalman filter and also something called the extended Kalman filter, which is a version of the Kalman filter that you can use for nonlinear models. Yeah, so the Kalman filter, it's going to recursively update the model state and its uncertainty, and it uses a variance minimizing update step. So that means you make a Gaussian assumption. And what you expect is that the estimate will improve and the uncertainty will reduce at each update. Okay, so let's look at the problem now is that we are only talked about computing a single update. And we need to understand how to evolve uncertainty in time. And there is, in the Kalman filter example, which I will explain first, you use a linear equation for the error evolution. And so suppose now that you start with a linear model, and I use a scalar model just for simplifying the notation, but the truth evolves according to this model. So if you have the true solution at time k-1, then you have a linear model operator G, and you make a prediction at time tk. And the truth at time tk is this prediction plus the errors in the model. What we are solving is typically this one. We have a best estimate, an analyzed estimate at time k-1. We operate with the model operator, and we get a forecast at time tk. Okay, so if this is the true evolution and this is our approximate evolution, then if you compute the difference, then we can have an evolution of the errors. Okay, and so this one minus this equation minus the numerical model equations, we can write like this. And if we square this equation and take the expectation again, then we get an equation for the full error covariance or error variance evolution. And what you have here is just the forecast error covariance matrix, or error covariance, forecast error variance in this kind of case. Here you have the model operator twice, and you have the analysis error variance. This is the model error variance, and this term we assume is 0 because we assume there are no correlations between model errors and estimate at time k-1. So this one disappears. So that means you have an equation for the error covariance evolution, and we write it like this. I think in vector form, we can then write the full Kalman filter like this. You have a linear model, you have a state vector, you have the analysis at the previous time, you have the forecast at the current time, and you have a linear model operator. The error covariance equation becomes this one here, and as you have G and G transpose. And then, given these predictions, you can compute an update with the new, based on the new measurements, like this, and you can update the uncertainty. And then, after having done that, you plug them in here and you continue the integration till the next time. Okay, so what can we say now is that this equation propagates the errors. So it will advect errors with the flow in a flow model. And it adds a contribution from the model errors at each time step. This equation computes an update, and this update is moving x closer to the measurements. So the larger this difference is, the larger the update is. If the measurement errors are 0, then you interpolate the measurements. If the measurement errors are going to infinity, then there is no update, basically. So this matrix gives a kind of weighting of the different residuals, so the different the updates from the different measurements. And since here you add covariance functions, it means that you get smooth updates, because this is the covariances are smooth as a function of x. No, yeah, a function of the spatial coordinate. So you add a smooth function for each of the measurements to your x to get the update. And I will have an example starting now. This is, I use a linear advection equation and I have a periodic domain. So that means I start with some random reference solution. So it's a wave and it propagates through the domain and then it repeats itself. So it's cyclic boundary conditions. Yeah, I have an initial variance. I have 4 measurements taken every 5 time units. And I will show one example without and one including system noise. And so this is my example. So I have the red curve here is the true solution that I'm trying to estimate. Everything is propagating to the right in this direction. And the blue curve is my estimate from the Kalman filter. And now I have these measurements and I have computed one update. This is the initial variance equal to 1. But then I have, from this first update, I have reduced the variance at the measurement locations. So you see that the blue curve is close to the red curve at the measurement locations, and it's further away at the other locations. If I continue the integration now, then we will see that the wave propagates in this direction, and the information for the measurements will also propagate in this direction. And that's what we see here. So now I have computed 30 updates, and I'm quite close to the truth all the way down to here. And at this part, the information from this measurement hasn't reached yet. So here I have still quite large errors equal to 1. And this repeats itself for all of the measurements. And I can continue the integration, and this is after 60 updates. And you see now that I have a quite good estimate of the reference solution from only measuring the solution discretely in time at these 4 locations. And also you see that now the information has actually propagated from this measurement all the way up here and about to this point. So you have a really good estimate with even lower variance downstream of the measurement here. And of course I can make this a bit more complicated by introducing model errors. Again, we have computed the first update and now everything looks the same. But here I'm propagating errors downstream, but I'm also adding errors representing the model errors, right? So that means the errors are increasing linearly going downstream. So I have larger errors here than close to the measurement. And I can again continue the integration. And again, you see that now I reach this quasi-steady solution where errors are has minimum at the measurement location and then increases linearly until towards the next measurement. The reason these are not exactly straight lines is that I use the ensemble Kalman filter to actually compute the solution, and there are some sampling errors in it. But the solution should be identical with infinite ensemble size. Okay, and then of course when you have examples like this with linear dynamics, it's really promising, and it kind of replicates what you want to do, or it is an example of what you want to do in real dynamical systems with more complex nonlinear models. And of course, the Kalman filter is famous. It has been used a lot in control theory and with weak nonlinearities. And it was also one of the methods of choice in metrological oceanographic applications when we started developing assimilation methods back in the 90s. Okay, this is an exercise. I let you think about it for a few seconds, but what is the Kalman filter solution for the linear inverse problem? So again, we have the xdt equals 1. We have an initial condition. And then we have a final condition, which I just say is a measurement at t equals 1. So if you want to compute the Kalman filter solution for this problem, what would that be? If someone is writing quickly, then okay. So let's show you what we get. We know that if you solve the initial value problem, then you get the solution. XF is equal to t, and that means the solution at t equals 1 is just 1. So XF is 1, okay? And then we have the error covariance equation, and that's just the initial variance plus the model error variance. So these were both C node. So then you get 2 times C node. And we have the update equation, which is this one. So we put C node here, 2 C node here. And then the measurement is equal to 2. The forecast is equal to 1. So 1 here and 1 here. And you get 5 over 3. And 5 over 3 is exactly the same value as we had before. It's this value. Okay, so in the Kalman filter, you would start here. You will integrate forward in time. You get here. You compute an update that moves you here. So that means at the final time, the solution is exactly the same as you would have from this variational formulation or the inverse problem. And but it's only true if you treat the model as a weak constraint. Okay. And this is good because it means that there is some consistency between all these methods. Okay, so what happens if you have a nonlinear dynamics? During my PhD, I worked a lot on using extended Kalman filters. I wanted to see if we could use extended Kalman filters with nonlinear ocean models. And extended Kalman filters, the only difference with the standard Kalman filter is that since the model is nonlinear, you cannot derive the error covariance evolution in the same way. Again, what we would have is that given a true state or true solution at time tk minus 1, the true prediction is the model prediction of this true state plus a model error. And our numerical model evolves again according to this equation. G of x analysis gives you a forecast. You compute the difference between these two. And now you see that you have since you have a nonlinearity, you cannot combine these terms directly. So what you do is to compute this difference equation. Then you evaluate this term, G of x true, around XA. You use a Taylor expansion for that. So you write this as a Taylor expansion, and the problem with the Taylor expansion is that it has infinitively many terms. And if we insert this expression in here, you see that G of XA disappears. You have the derivative of the model evaluated at XA, so that's a tangent linear operator here, times this difference. And then you get second order derivative, so this is the Hessian. And this just continues, right? It's an infinite series. And so that means the difference become something like this. And what we can do now is to square this equation. So you square this term to get CF, the error covariance for the forecast error covariance. It's this first part. You square this term to get what you have here. And here you have the analysis error covariance. And then you get infinitively many terms with higher order moments. And then you have the model errors at the end. And if you look at this equation, it's exactly the same as we had before. It's the model operator 2 times operating on the analysis error covariance matrix. But then we have all these higher order terms. And if we neglect these, then it means that we get the extended Kalman filter. And so that means we close this system by neglecting all these higher order moments. And that's really the simplest closure we can make. And now we can actually solve this, use the Kalman filter update equations together with these 2 equations. So you have a full nonlinear evolution of the model solution, and we have a linearized evolution of the errors. And the surprising result with this was something I also did during my PhD. I used a nonlinear quasi-geostrophic model, and then I implemented a full extended Kalman filter with this. And I made an example where I had a stream function, a kind of steady stream function solution with curved and shared flow. And so this is just my model domain. So this is, it's a gyre or an eddy in the ocean, and you have flow going in this direction actually, along this stream function. And the initial error variance was equal to 1. So it was this blue color everywhere. And then I just run the system forward in time, and no measurements, nothing. It's just pure error evolution. The initial variance was equal to 1, and I'm advecting errors along these streamlines. And what I see is that I get a very strong error variance growth, and it's actually an exponential error variance increase with time. And the reason for this is that, well, by making the linearization in the error variance evolution, this leads to a linear instability and exponential error growth. So all these terms in here that I have neglected, the role of them would be to saturate this error growth, because like in the atmosphere, or you can imagine that you have high pressures and low pressures, but there is a maximum value. Maximum high pressure is a minimum low pressure that you will never exceed. So the errors will only increase to a certain climatology, and then they will be steady. And it's this saturation of errors that is missing in this equation, and I've neglected the high order terms. So, and this is not good news, because it means that you need a lot of measurements to control this increase in errors. Otherwise, your system just goes unstable. Okay, so to summarize what we have now, the Kalman filter is the optimal linear filter method. So if you have a linear model and linear measurements, it gives the optimal solution. You need to store a matrix, the error covariance matrix, which is n squared. So that means you have a problem for large models. You need to integrate 2 end models. So for each column in the error covariance matrix, you need to solve the model twice, the linearized model twice in the extended Kalman filter. And then in the extended Kalman filter, you apply a closure approximation, and it requires the implementation of the tangent linear model, which is just the derivative of the model with respect to the state. And this too simple closure may lead to linear instability. So if you have unstable underlying dynamics, then you have unbounded error variance increase. So basically, it doesn't work for strongly nonlinear models, and we need a better alternative. This is a really good time for a break, right?
Yes, I would say so.
Yeah, because I'm following exactly the schedule, I think.
Right. So we'll proceed to serving coffee to everyone. That may take a while. So
yeah, there are cakes and waffles and.
Get yourself your own coffee, and that will save us a lot of time. Yeah.
So in the next session, I will talk about ensemble Kalman filter, basically.
Thanks. We see you in the quarter.
Yeah, that's fine. Okay, I just leave this like this.